double integrals, triple integrals. And so again, it's a generalization of things you learned either in Calc 1 or Calc 2, almost everything we're doing. And sometimes it's multiple problems because you have to iterate. You have to do work at the inside integral and then work your way out. And there was an idea that I think is probably the most important idea I teach in Calc 1, getting people ready for Calc 2, which is substitution. The idea of U substitution, right? Where you change, and then eventually, I guess in Calc 2, you guys do trig substitution. You do other kinds of substitution, right? So today, what I want to talk about is substitution in the world of multiple integrals. And so double integrals, triple integrals, or more, but we're not going to go any more than a triple integral. Okay. And just talk about what's really going on. I know that the book waits on this. Oh, is this 15? Yeah, 15:7. Sorry about that. I know that the book waits on this until the end of the chapter, but I think covering it now is nice. It kind of shows you that these are not magic formulas that we're using. You're going to understand what's really going on, and that's my reason for wanting to jump ahead. Plus, like I said, with the project, it just seems really nice to free up some time next Monday so you can share with each other what you've been working on. So, looking at the book here, there's a couple of nice things they do. They say, okay, remember the world of substitution? Let U equal the stuff in parentheses when you look at a problem, and so they're letting U equal what? 2x plus 1, right? What we didn't show you in Calc 1 was this picture. Basically, we didn't show it to you because we had enough to worry about. We didn't need to show you this. But now we want to. So what's going on in this picture in the book? Well, on the left, you have an XY plane, but on the right, what do you have? A UY plane, right? This is a square root function. This is 2 times the square root of 2x plus 1. That's why when I plug in a 2, let's see, 4 plus 1 is 5. I get 2 square root of 5. That's ugly. When I plug in a 4, there we go. 8 plus 1 is 9. The square root of 9 is 3. Should be going through 4 comma 6, which it is, just off the map. Okay? But what we do, when we do the transformation where we say U is 2x plus 1, this is the thing we integrate. Right? We integrate this. What's really interesting is that these areas are the same. Oh, as long as I did what? Yeah, the bounds. The bounds used to be 0 and 3. How do you change the bounds? Well, you plug in a 0 and you get 1. You plug in a 3 and you get... I'm sorry, you plug in a 1. And if U is 2x plus 1, you get 3. And so that's where this is. Right? Do you guys... how many people follow the picture? What's going on here? Okay. So that... they could have shown you when they taught you the substitution, but we didn't. But it does come in extremely handy now that we're in Calc with multiple integrals. Okay? We're going to be doing transformations of the plane. Transformations of the plane. So, how does this work? Remember region R? It seems like in this world of 3D calc, the most important thing is the region R, which is underneath the surface. We say we're integrating over the region R instead of over an interval on the line. What if region R is ugly? Well, the idea is there may be a transformation, capital T the book uses, that will change you from an ugly region to a nice region. I used the words vertically simple or horizontally simple. And so that's what we're going to end up doing. I want to give you an example or two that'll kind of guide us along what's really going on here. So let's kind of go to the notes here and see if we can do that. So if I start with this, suppose I'm going to, let me use gray. I'm going to do the double integral over my region R, where what I'm going to integrate is, let's say, 7xy and then dA. Where region R is bounded by 4 lines. And the 4 lines are going to be 2x plus 3y equals 1, 2x plus 3y equals 3, x minus 2y equals 2, x minus 2y thank you, equals negative 2. So what happens here, if you graph this region R, right? And again, I know there's a surface, right? 7xy is some kind of surface, right? Z equals that. But I just want to talk about the region R in the xy plane. Well, I guess, let's see, 2x plus 3y equals 1. Well, okay. It goes through like 1/2 comma 0, right? So if this is 1, it would go through 1/2 comma 0 and 0 1/3. I guess the point is that that first line looks something like this, and the second line is just shifted up to, looks something like that, right? And now the other lines, let's see, go through 2 comma 0. So the other line might look, and I guess it goes through, so it goes through 2 comma 0 and 0 comma negative 1. So here's 0 negative 1, and here's 2 comma 0, and so something like that. And then I guess this one goes through 0 comma 1, and so it looks something like that. And so this parallelogram in here is my region R. Something like that. You guys see it's a parallelogram? Let me ask you this. If you had to pick, you have this dA, right? And you get the choice of integrating dx dy or dy dx, what would you say? I see you shake your head. You say no, and that's a good answer. No, I don't want to. I don't want to integrate dx dy or dy dx, because why? You have to split it into multiple integrals, 2 or 3. I mean, I'm not sure if those vertices line up exactly, right? You see the problem, right? We've done this enough now that this is kind of an issue. So sometimes the shape of the region R dictates that what we really want to do is we want to do a transformation, a change of variables similar to what I demonstrated in that first picture, okay? And your book is going to talk about exactly what is the theory here behind this, okay? Behind these transformations. And so I'd like to show you just a little bit. The image of a transformation. Bless you. Polar to rectangular, 1 to 1. No, this is a really nice math word, 1 to 1. The idea of a transformation being 1 to 1 means that basically for us guys, you can go both ways. It has an inverse. I can transform it and I can transform it back. Okay? And I think that's all I want to say about it for now. And then here is the big deal. Given a transformation, x equals a g of uv and u, should be a y there, y equals h of uv, where g and h are differentiable, the Jacobian determinant or Jacobian of t is blank. Okay? And so we're going to write this either as juv or this. Basically what this gives you is what you might call the fudge factor. The fudge factor. Remember back in Calc 1? Here, let me show you the fudge factor in Calc 1, right? I mean, when you had to integrate the cosine of 2x dx, you guys now know what's that equal?
1/2 sine 2x.
Yeah. And the big thing that took us a while to understand in Calc 1, that 1/2, right? How do you explain that to someone, where that 1/2 comes from? Well, take the derivative, check. Well, what rule forces me to put that 1/2 there? When I take the derivative, I have to use the chain rule. So the chain rule backwards is what substitution is all about. Well, basically what I'm doing here, guys, is I'm going to take the chain rule and I'm going to up it a dimension or two. How do you up the chain rule or the substitution rule? And the answer is that instead of just multiplying by the fudge factor, I'm multiplying by what's called the Jacobian. And the best way to define the Jacobian for you is as the determinant of a matrix. And you guys have done that before? Yeah? I think you have, because how did they do cross product for you guys? Did we define it as the determinant of a matrix? So I think we've done it, and I think in our books says, hey, you've done this enough to define it this way. I've seen other books that don't define it this way. They like write out without a matrix all the crazy. Matter of fact, when determinants were invented, there were no matrices yet. It was just kind of this crazy combination of all the variables. Okay, which works. I think that's fascinating. So anyways, we're going to try and use this now, and then go ahead about my integral. Okay, because the theorem says if you want to change variables and integrate, and by the way, I don't like the statement of this theorem exactly, because they're writing dA here and dA here for two different regions, R and S, and those can mean two very different things. Okay, but I do like this. They say, hey guys, multiply by the determinant of the Jacobian. That's really what you want to do. The Jacobian matrix is a matrix filled with partial derivatives. That's what it is. This doesn't do much unless I'm doing an example. You'll notice I'm in the middle of one. Okay, so let's do it. Here we go. I'm going to make a substitution. And the substitution should make sense to you. I'm going to let u equal 2x plus 3y. And what do you think I'm going to do? I'm going to let v equal. You're right. I'm going to let v equal x minus 2y. And what I'm going to do now is I'm going to create a region S. So T is going to be the linear transformation. Actually, it should be the other way around. Well, let's see. What I want to do here is I want to write down s. And I guess what you can do, guys, is you can just take these four equations and rewrite them, right? These four equations, if I make this transformation, what would they become? Well, u is equal to 1, u is equal to 3, v is equal to 2, and v is equal to negative 2. Yeah? And so now, instead of the xy plane, what I have is I have the uv plane. And the beautiful thing about this region, which I'll call S, is this is going to be both vertically simple and horizontally simple. So u equals 1 is right there, and u equals 3 is right there. So I guess my region goes through u equals 1 and u equals 3. And then on the v-axis, it goes through negative 2 and 2. And so this is my region S. Make sense? I like integrating that way, with that as my region. So now what I need to show you how to do is, how do I change this integral to a double integral over S? Well, here we go. The double integral over R 7xy dA is equal to the double integral over S times what? Well, let's see. I guess I have some work to do. Because if u is equal to 2x plus 3y and v is equal to x minus 2y, what I really want to know is, how do I write x? What do I write for x, and what do I write for y? That's what I really want to know. Does that make sense to you guys? But we have a system of equations, and so we ought to be able to go through and solve. So let's see. Take that system. Running out of room. Time to do some work somewhere else. Here we go. Let's take this system and let's explore it down below the picture. So what I'll write is that, well, let's see. When you look at the system of equations, if I said to you guys I want to eliminate the x's, you could if you added the equations, but first you'd have to multiply the second equation by what? Negative 2. So that's an addition method way of doing this, right? You can see that if I do u minus 2v, then the x's will drop out, right? Because you'll have, well, u is 2x plus 3y minus 2 of the v's. And so what does this equal? Well, the x's drop out. I guess I get 3y plus 4y. I get 7y. Yeah? And now, what about if I want to get rid of the y's? What do you think I ought to do? Something. Whoa. I guess that's one way to get rid of the y's, right? Just turn off the power. Better idea. I mean, you know, if you multiply the top equation by 2 and the bottom equation by 3, we'll have a 6 and a negative 6, right? So let's try that. Let's go 2u minus 3v. And could you guys tell me what that is? So here the y's are going to drop out, right? The 6y and the minus. Oh, wait a minute. It should be plus 3v. Otherwise, that won't work. There. Thank you, Alex. So now the 6y and the minus 6y will drop out, and so what does this equal? Ah! Beautiful. These sevens are lucky 7 is showing up everywhere. What a nice problem. All right, so let's see how this all works. So what I can do now, right, is I can say that this equals, let's see, 7. Well, wait a minute, wait. Let me slow down. Instead of doing that, here, where it says 7x, what can I write? I can replace that 7x with what? 2u plus 3v. That's nice. Now where it says y, oh, not so lucky. What does y actually equal? I guess it's times 1/7 of u minus 2v. You guys with me? And then times what? Well, here's where I'm going to write down j. I'll put a little circle around it. And I'm going to say I ran out of room on the paper. But you need to multiply by j, the Jacobian. That's what this theorem is saying right here. When you make a change of variables, we need to compute the Jacobian if we have x is something and y is something. Actually, I guess we have two maps, right? We worked out what x and y equal right here. Maybe not so explicitly, but let's do it. Let's say very clearly what x is. X is 1/7 of 2u plus 3v, right? And y is what? I did it in green last time. Y is, that's it, 1/7 of u minus 2v. So, looking at the book, the Jacobian of u and v, okay, the Jacobian of u and v is defined to be or maybe the determinant of the Jacobian, because sometimes they'll write the bars, is defined to be the determinant of the matrix. And so the book will also write this. They'll write partial of x with respect to u. Let me do it the same way they do. It doesn't actually matter, but then they're going to say partial of x with respect to v. They'll say partial of y with respect to u, and they'll say partial of y with respect to v. Okay? Another way this is sometimes written is that notation. You'll see shorthand this. You'll see partial x comma y over partial u comma v. And this is just funny notation for this determinant. Okay? You don't need to write that. You could just say Jacobian. If you want to just put a j and circle it like I did, I'm okay with that. Okay? But this is the fudge factor, let's say. So we have some things to fill in, right? What does this equal? Well, this particular example, I want you to understand it's a first problem because in some ways it's very basic. Because what is the partial of x with respect to u if we're talking about this equation here? Well, the v goes away. We treat v as a constant, right? So it's just, yeah, 2/7. In general, that's going to be a function, not a number. But in this first example, that's all it is a number. You guys get that? So what about over here? dx dv would be 3/7, right? And then dy du would be 1/7, and dy dv would be negative 2/7, right? And so I can work out what the Jacobian is. The determinant would be, let's see, negative 4/49 minus 3/49 equals, oh, I love it. Not only did I get negative 7/49, but I can simplify that to be, they were really nice to me with this example. Negative 1/7 is what I have to multiply that by there. And so when you look at this thing, right, what does this equal now? Here, maybe we can write it out. This equals the double integral over s of, well, I guess I have negative 1/49, right? Oh wait, time out. Notice that there's bars here, okay? I want these to be an absolute value so that I end up multiplying by 1/7. Okay. So I get 1/49 times what? Well, times 2u plus 3v times u minus 2v, and that's dA. So it's a little bit of a mess, but I think from this point on everything should work fine. This is going to be equal to the double integral over s, 1/49. I guess I have 2u squared. Now plus 3uv minus 4uv, so minus uv minus 6v squared. And I guess, well, I have a choice to make. Do I want to go dx, not dx dy anymore, what's the choice? We either go du dv or we go dv du. So I'm going to go dv du. Let's work that out. So let's see. If I'm going to go dv du, this double integral is 2u squared minus uv minus 6v squared. I'll put the 1/49 out front. Now, the hard part for you guys, I'm guessing, lately has been just getting the limits. Or maybe we're doing okay on that. I don't know. Let's see. Do you guys work outside in or inside out? Or either? Don't know? Okay. I like to work outside in, personally, when I'm setting the limits. But then when I integrate, you have to go inside out, right? So when I'm going outside in, one of the nice things is I look at, in this case, u. And the nice thing about working outside in is that these things are going to be numbers, right? So what are the limits for u here? Well, it will be 1 to 3. And then the inner, I guess in this problem it really doesn't matter. In general, these are functions, right? So when I'm looking at the v's, right, these are functions above and below, but here it's just v equals negative 2 to v equals 2. So yeah, this is an easy one. But it's a long one, right? There's no short problems in Calc 3, Chapter 15. Yeah, I assigned 10 problems. That's plenty of work, right? So let's see. We have 1/49, integral 1 to 3. As I integrate this thing dv, what happens? I get, well, 2u squared v, right? That becomes a v. And then this becomes minus 1/2 uv squared. And this becomes minus, would it be 2v cubed? Okay. And then that goes from negative 2 to 2, and then we'll integrate du after that. Paul, you're running out of room. All right, well, let's flip the page a little bit here. So I just had, again, 1/49, integral 1 to 3, and I had all this stuff. So I will plug in my positive 2 and then subtract what I get when I plug in my negative 2, and then I'll integrate du at the end. So when I plug in the positive 2, and again, let me just show you my expression I'm dealing with. It's right up there in gray on the right, okay? So you can follow along. When I throw in the 2, I get 4u squared, and then I get, let's see, that's 4 over 2 is 2, so minus 2u, yeah? And then when I throw in that, 2 cubed is 8, and times 2 is 16, so minus 16. That all look good? And now I'm going to throw in negative 2 into the other expression. So that's minus 4u squared here. But here, when I throw in the negative 2, I think that's going to cancel out, right? Because you just get minus 2u, you're subtracting. And then I get, when I throw in the negative 2 there, I get a positive 16 because there's a negative negative, so plus 16, yeah? How we doing, guys, okay? So this is 1 over 49, integral from 1 to 3 of what? I guess it's going to be 8u squared minus 32 du, yeah? So this is 1 over 49 times, well, when I integrate du, this is 8 thirds u cubed minus 32u. And again, I'm going from 1 to 3. So let's see, this is 1 over 49 of what? Well, when I plug in the 3, there's a canceling that happens there, so it's just 8 times 9, 72. When I plug in the 3 here, I'm subtracting 96. Right? And now minus, oh, well, when I plug in the 1, that's easy. It's just 8 thirds minus 32 here. Yeah? So let's see, 72 minus 96, right, is, well, I'm done. Let's just call this 16 over 147, and I'm going to say I used a calculator at that point. Okay. But there's your first example of a transformation, a Jacobian, a double integral. So that's kind of good. We saw a double integral now. Any questions so far? Okay. So I guess next example, there is one more question to ask, okay, which is why? Why do you have to multiply by a fudge factor? I mean, maybe the easy way to see it is to just kind of look at that picture we did, right? The fudge factor for us was what? 1/7, right? And really, that was the transformation from, if you look at it, from x, where x's and y's are equal to uv's. I guess what I'm saying is this area is 1/7 of that area. That's really what I'm saying. Okay, so when I said this arrow is kind of the wrong way, that's really the map I'm looking at, which is interesting. Think of it like this. I mean, guys, we're going to have lots of transformations that are not boxes, and I'm not going to explain all that. But you know, when you have a box, what happens when the corners start giving out? Well, it turns into a parallelogram and you lose area, right? What the Jacobian is telling you is how much area you're losing. It's this quote rectangle instead of a rectangle. And that transformation is measured by the Jacobian. But I think I do want to do another example. So let's try this. Suppose we have the following ellipse. Well, actually, okay, so first let's write the integral and then I'll give you the ellipse. So double integral over r of x squared plus y squared dA. And again, I'm going to give you what r is. R is the region bounded by, let me write it this way, x squared plus y squared over 4 is equal to 1. Maybe I'll write it as x squared over 1, right? But this is what shape, guys? Yeah, is it a fot or a fog? Football on the ground or football on the tee? Yeah, it's on the tee, right? Because the y's go up and down 2, and the x's only go out 1. And so my region R looks like this. Okay? Now, can I compute this integral without a transformation? Absolutely. This one is vertically simple, horizontally simple. But it's going to be worth it for us to look at how this works, okay? What I'm going to do is I'm going to do a transformation where I'm mapping this onto, any guesses? I don't really want an ellipse. You know what I want instead? The good old unit circle. Because then, hey, when you're looking at this thing, how are we going to integrate it? Polar coordinates, going to save us a lot of time. But polar coordinates for this ellipse, not pretty. Polar coordinates for a circle, beautiful. So let's figure out what should the transformation be to turn this ellipse into the unit circle. Well, we could do that, right? You just have to tell me what x is going to become and what y is going to become. Right? I mean, here's x and here's y. Right? So we have to relate those to u and v. You know, eventually you may jump right to this, but I guess what we're really doing is let's talk about how u and v are related to x and y. What does u equal?
X squared.
Oh, you could. Hey, what's the equation of the unit circle? Let's go with that. We want u squared plus v squared to equal 1, right? Duncan, an idea? Yeah, make u equal to x, right? And make v equal to what? Well, not y. We want it to be half of y, right? Or in other words, x is equal to u and y is equal to what? 2v. See, it's twice as tall as the unit circle, but it's exactly the same in the x direction or the u direction. Now, let me go through what's going on here. Last time, what I did was I figured out u and v, and it was not this simple. We had a system of equations that we had to play around with for a long time. But in this problem, what a simple system to solve. X is the same as u, and y is just 1/2 v. Do you guys see that? So that's kind of nice. We're going to use that to get the Jacobian, J. Right? You guys want to try it? See if you can compute the Jacobian. So again, the way the book is going to write it is they're going to put absolute value of J of u and v. The Jacobian is a function of u and v in general. Although, again, this is another example where it works out really nice, right? It's the determinant of partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, and partial of y with respect to v. Why does this one work out so nice? Yeah, because, I mean, you have zeros, right? X doesn't have any v's in it. Y doesn't have any u's in it. So you have a 2 here and a 1 there. Is that what you have? No, other way around. A 1 there and a 2 there. But either way, we're getting 2. Okay. So what does that tell me? That tells me that when I do this, right, I can rewrite this problem, which is in x's and y's. This equals double integral over s. Oh, I'll need to change the integrand, right? But then what do I multiply by? I multiply by 2 dA. Guys follow? So what goes in here? Good. U squared plus, since the y is being squared is 2v, yeah, it'd be 4v squared, I guess. Right? Okay, so from here on out, I guess I just do the details. Let's finish it, though, because, I mean, you guys are telling me you're having trouble with the triple integrals, and I think a little more practice, a little more examples, not bad. So let's see. I guess, would I bring my 2 out front? Probably. It's just a number. I'd probably just put it out here. Okay, so we want to integrate u squared plus 4v squared. Which way? du dv or dv du? Doesn't matter to me. Why don't I do... Oh, wait a minute. I don't want to do du dv or dv du. Well, yeah, let's do it. Let's... I mean, the point was I wanted to go polar, right? Because otherwise I have to write what this function would be, right? And this function. Okay, so let me write dA. And now, let me write S. Instead of writing du, dv, dv, du, okay, here we go. Polar coordinates. So what do we have? 2. So let's substitute now. What's the substitution I'm making? I'm going to say that u is equal to, if we're going to go polar, you know what I'm going to let u and v equal? Yep, because they're taking the place of x and y, right? Our cosine theta and our sine theta. Okay, so now let's see what we have. We have, I guess this is r squared cosine squared theta plus 4r squared sine squared theta, right? And where it used to say dA, what do I have to put? R dr d theta. And now, let's see what we're integrating from where to where. Well, the thetas, I like to work outside in, would go from 0 to 2 pi, right? And what about r's? I guess that's just 0 to 1, right? So that's kind of nice. Okay, so if it were me, I would factor out the r squared, you know. So it's just r cubed, right? 2 integral 0 to 2 pi, integral 0 to 1. And so here I have cosine squared theta plus 4 sine squared theta. And so I have r cubed dr d theta. Okay. Moving along. Well, okay. 2 integral 0 to 2 pi. Now, when you integrate, maybe I should have done this, guys. You see that 0 to 1? Are you okay if instead of putting that 0 to 1 there, I actually wrote it here? Because that's the integral that's associated with the dr, right? And all this stuff is being treated how? Right. I can't pull it past this one, but I could pull it past that one. You guys follow that? Good. Now, what is it that we're integrating? Well, okay, so a couple things happen. Here, let's do this. When you integrate r cubed dr, you get 1/4 r to the 4th, right? Plug in your 0 and 1. Are you guys okay that this is just 1/4? Yeah? I'm just trying to speed us along. And also show you tricks of the trade. What about this? Well, cosine squared plus sine squared is what? 1. So are you okay if I write 1 plus 3 sine squared theta? Is that okay? Because it's cosine squared theta plus sine squared theta plus 3 sine squared theta. Yeah? That's a nice trick. Then,
Could you move your paper down a little?
oh yeah, sorry. Thanks, Alex. So now, let's see. We're almost done. I'll bring that 1/4 out with the 2. So if I do that, I'm at 1/2. Right? And everything else in here is a d theta. So let's integrate this stuff d theta. When we integrate 1, we get theta. Yeah? Because we're integrating d theta. It's kind of like you usually get x when you integrate 1. When you integrate 3 sine squared theta, you get 3. Now, I'm trying to speed us along. How do you integrate sine squared? There's a trig identity. We used it on the homework, I'm sure of it. Do you guys know what? Here, I'll write it up here in gray maybe. Sine squared theta is equal to what? The power reducing formula, they call it. 1 minus cosine of 2 theta over 2. I'm glad I wrote that down. I don't think we know that one. Have you seen that before, guys? Let's do a test. Do you guys know what cosine squared of theta is? It's almost the same as this. It's just plus. 1 plus cosine 2. So these are really nice formulas to know. Things like sine squareds come up a lot because, well, obviously, because r squared, right? X squared and y squared would be r squared cosine squared and r squared sine squared. So these things come up a lot. Well, I guess what I'm saying is, if I know that identity, I can probably integrate this without writing much more down. So let me just fill that stuff in. And then we're going to have, let's see, this is going from 0 to 2 pi. So let's see. When you integrate 1/2, what does it become? 1/2 theta. And now, when you integrate this, negative cosine 2 theta over 2, I hope you're okay with it being, let's see, what's the antiderivative of cosine is sine? So it'd be negative 1/4 sine of 2 theta. Why is it negative 1/4? Yeah, that's that chain rule thing I pointed out way early in the class. Remember that? Guys know what to do now? Plug in the 2 pi's and plug in the zeros. When I plug in 0, what happens in this problem? Is it true everything's gone? What's the sign of 0? Good. So everything's gone. Hey, sine of 2 pi, that's the same also, right? So the only thing that's going to give me any volume, let's say, or area, is when I plug 2 pi in for this theta and that theta. And so I'm going to get 2 pi, and then here the pi's cancel, so plus 3 more pi is, the final answer I think is 5 pi over 2. Does that look right? Or 5 halves pi, you might say. I think it is to our advantage to cover this really before that, in a way. On the other hand, almost every book does that last. They kind of say, well, who cares about Jacobians? They do. They say, you're a bunch of engineers. Just teach them the calculus, Paul. They don't care about Jacobians and transformations. Oh, okay, I understand. But I feel like it's nice to make it mathematic over magic. Okay? And let me show you this little discussion, which I think is really interesting. Where? Not there. Here, the book. When we go through this Jacobian stuff, and they do a problem kind of like I did, and another one kind of like I did. Look at that one, guys. Little curves. This is interesting because now your Jacobian ends up not being just numbers. I don't want to work it all out, but I'll just show you. See how you get functions of u and v there? So your Jacobian can be a function of u and v. So then you have to multiply by a function of u and v. You see that? Kind of good to know. And when they work it out, it still works. It's just you multiplied by some other function instead of a number. Okay? So they say, oh, change of variables in triple integrals. Remember triple integrals? Let's show you how they work. And they kind of go through here. I'd like to work through an example for you of that. But I think before that, don't they show it? This. The image of a transformation. Example 1. Right? Isn't this like our favorite transformation? We've done it more times than any other. You've been doing this for a year, right? You did this back in Calc 2 for sure. Maybe even before that. You said, you even told me in the last problem, let x equal r cosine theta and let y equal r sine theta. But what you never did before is you never computed the Jacobian of that. Well, let's do it. Well, no, the book does it for us, so let's look at what happens. If you transform this square into this circle, you're doing x equals r cosine theta, y equals r sine theta. Oh, do they do it? Where is the Jacobian, guys? It's got to be done here. Yeah. Here it is. The Jacobian of polar to rectangle. They say x is now a function of r and theta, and y is a function of r and theta. And so look what happens when they compute the Jacobian. Right? Like if you take the derivative with respect to r of r cosine theta, you just get cosine theta. But if you work it out, look what you get. R. Why is that important? Because all week long, when we've been transforming a double integral from dx dy or dy dx, we say, no, we want to do polar. What do we always write? R dr d theta. R. Right? That's the key. You need R. Now, there are similar transformations underway for cylindrical, which I'm going to have you guys work out for homework. and the one that's more foreign to us, spherical. And so I thought that would be our last example. Let's compute the Jacobians for a transformation from spherical to rectangular coordinates. And then I think that'll be kind of cool. So, that means I have to go back to this section. You asked me, Sullivan, do I have everything? Almost. But I do want to do just a little bit more with spherical coordinates. I did show you guys what rho, phi, and theta were, right? The picture in the book is right here. Let's see. Yeah, rho, phi, and theta are represented here. Right? So again, theta is nice. Theta is just, what it's always been. Distance from the x-axis. But phi is from the North Pole. How far down from 0 to pi over 2? You guys follow? Okay. So, we also see from figure 15.56 that x equals r cosine theta, and then what do? This is really nice. X is equal to rho sine of phi cosine of theta. Do you guys see that? It says we can get that from this picture. So personally, I need a little more help. I need a pencil and paper also. So let's do that. Here, I want the book up there, but I want my pencil and paper, and I want to go back to spherical coordinates, right? So let's see. When I do spherical coordinates, I do understand that x is equal to r cosine theta, where r, see r on the picture? R is in the xy plane. It doesn't go up or down at all, right? It's the base of that blue right triangle, but it's also the hypotenuse of another right triangle. You guys see it? So I guess the next thing is, what do? They say, well, okay, they say that r is actually equal to rho sine of phi. So let's understand, why is that true? Why is it that r can be replaced with rho sine of phi? Do you see that from the picture? Well, they're focusing on the blue triangle. So the blue triangle, I think, looks something like this, where that's a right angle. This is the hypotenuse, right? So that has length rho, and this has length r. And then, what's phi? Phi is distance from the north. It's angled down from the North Pole. Well, they claim that this phi is congruent to that phi. Can you tell me why that's true? Why is this angle in the blue triangle equal to phi? Sure, geometry reasons, alternate interior angles. That's a good reason. So now if I say, okay, well, let's look at that phi, I can say that the sine of phi is opposite over hypotenuse, right? So the sine of phi would be, well, r over rho. So yeah, r is equal to rho sine of phi. Yeah? You guys with me? And let me just say that x equals rho sine phi cosine theta. Y is equal to the point of this huge calculation. And do they do it? I don't think they do. I think they just kind of give it to you, which is why I wanted to do it. Is when you're going to do integrating in spherical coordinates, the Jacobian ends up equaling. Let me show you the formula right here. This is the answer that huge mess is going to simplify to. That's what we're going for. So remember how we always did r dr d theta? Well, here it's not r, it's you need to multiply by rho squared sine phi when you change from dv to an iterated integral. That's the point. So do you memorize that? Yes, you memorize that. Or you look it up. That's one you get, because you don't want to work out the Jacobian every time. But I want to show you that you can. And, well, apparently we need more time. Okay, so you'll notice, like when they start doing their examples here, very first thing they're going to do, guys, this dv is going to be replaced with, here's your rho squared sine phi, and then d rho d phi d theta. Okay. The only other question is, where did that rho to the negative 3 come from in this example? And they could try to show you here that this is rho squared, right? And it was raised to the negative 3/2 power, so that's where rho to the negative 3 came from. You'll see stuff like that. They try to be nice with the integrand in this chapter. Because if they're not, it's hopeless. Right. All right. Let's look at Sullivan's problem. It was 15.4, number 47, you said?
I don't know. 47.
Oh, now you're changing your mind. I thought that was the one you asked about. 57?
57 is, I'd much rather see 57, honestly.
All right, let's see what we could do.
47 makes sense. I just,
Use a triple integral to compute the volume. Well, yeah, that should make sense. All right, 57. Because to compute volume, what do you have to integrate? If you want to use a triple integral to compute volume, what do you integrate, guys? 1. Okay. General volume formula. Find equations for the bounding surfaces, set up a volume integral, and evaluate to obtain a volume formula for each region. Assume that we have a bunch of constants here. So R is constant. H is constant. What a beautiful problem. All right, let's give this a shot. Nine minutes to make an attempt on section 15.4, number 57. Thanks, Don. So, okay, we have a sphere. And they're saying we have a cap of the sphere where, you know, this is R. This distance here, they're called H. Oh, I have to show it a little better. And it says, see if we can find the volume of that cap. And we're going to want a triple integral. You know, this one's going to be easier in spherical coordinates, obviously, right?
I tried to change it to polar after the first step.
Okay, well, let's see what we could do
That
here.
sort of worked, but not really.
Let's see what we can do here. So, let's see. The volume is equal to the triple integral over d. D here is the cap, right? Of 1 dv. And so the question is, how do we set up an iterated integral dx, dy, dz, dz, dy, dx, etc. Let me try dz, dy, dx. Is that what you tried, Sullivan, or no? Okay.
And then I went from r minus h is the low bound.
Right. Because it's also r when I go straight up here.
Yeah.
And so the bottom z level is really nice. Z equals r minus h is a plane down here, right?
Then the upper bound is, that's the square root of r squared minus x squared minus y squared, isn't it?
So yeah, I guess we have to get that, right? So this equation of the blue, right, the surface itself, we know that the sphere is x squared plus y squared plus z squared is r squared. And so what you just did is you solved for z. And so the boundary, I agree, would be, it's plus or minus, but we're going to use the positive, right?
Yeah.
Because it's plus or minus r squared minus x squared minus y squared. Yeah. So here we have positive square root r squared minus x squared minus y squared, and then the bottom is r minus h. Now, when we do this, I guess, what are we integrating over? We're integrating over. If I project this down, do you see we have a circle here? Does that make sense to you guys? So this double integral, maybe I should draw a picture of that somewhere, like down here below. Let's draw a picture of that circle, that green circle. This is underneath the cap, right? So maybe the other thing that's important is to notice, you know, another view of the sphere. Let me maybe make it a little bigger. Okay. Here is the cap up here. And I drew that this was R. But I guess I need to know,
The upper r,
yeah, I mean,
which is, yeah.
what is this distance here, right? It's not R, it's less than R. So what do we know? Well, this is where you told me that this is R minus H, right? So now I can solve for X, right? So X here would equal, well, the square root of R squared minus R minus H squared. You did that?
No.
No. Okay. So if we do R squared minus R squared, we get 0. And so I think what you're going to get is the square root of, this would be negative times negative 2RH. So you're going to get 2RH, and then we get plus H squared, but then we're subtracting, so I get minus H squared. Is that clear where that came from?
That makes more sense. And that's, yeah, that was not what I did.
So that, I guess, gives you the radius of this circle, right?
And then, okay, yeah. and then
So,
switch it.
so remember how I do this now. Switching to polar is probably a good idea at this point, because if not, what are we doing? We're going from, the x value would be negative square root 2r h minus h squared to positive square root 2r h minus h squared. Okay.
Do we want to use symmetry?
Oh yeah, we do. I'm just writing it out.
Okay.
I mean, you could argue this. Hey, Paul, if you can write it out, plug it in a computer, you're done, right? So I did the grays as functions of x and y. I did these, which are constants. What about y? Y is supposed to be just a function of x. Let's see if I can do that. Let's see if I can write down y as a function of x. Well, sure I can, because we know that the equation of that circle would be x squared plus y squared equals, well, I'll just say radius squared, because I already used capital R. I'm worried I might have already used lowercase r. I don't know. Okay? So what does y equal? Y equals plus or minus the square root of radius squared minus x squared. And that's the radius squared. So I guess if you asked me, hey Paul, what goes in the middle integral here? Okay, I'll fill in the bound on the lower bound here. It would be negative square root. Now radius squared would be this stuff, so it's 2rh minus h squared, and then minus x squared. So that's the function of x. Same thing without the square root, goes up here. It would be 2rh minus h squared, and then minus x squared. And so, plug that into an algebra computer, it'll work it out for you, huh? Or work it out. And I guess we're out of time.